All right. And with that, we'll take a moment here to introduce Yoon Ding, who's our next speaker, and comes to us from GSK, where Yoon's been involved in Dell chemistry for a very long time. She started her career in the field in 2004 at Praecis Pharmaceuticals that was eventually acquired by GSK. And played a key role in a number of different aspects that developed the technology, including the first clinical candidate that from GSK that came from encoded library technology. So Yoon, are you there? I'm not seeing your image. There you are. So I'll let you go ahead and start to share your slides. Are you sharing your slides, or is Mike going to take that on?
I'm sharing right now. Can you guys hear me?
You've got a bit of an echo, but maybe that's me.
Oh, let me try again. I'm using the computer speaker. Can you guys hear me? It's good or it's not that good? I can use the speaker.
Yeah, it has a bit of an echo.
Okay. First of all, let me try to. How about right now? Is it better?
Oh, better.
Okay, good. All right. I thought I shared my screen. Can you guys see my screen?
Yes, we can see it.
Okay, good. Let me see how this. Is it good? Can you see the title slide? Okay. All right, great. Thanks for the introduction, Tim.
There's an echo. Can you turn down your speakers?
Really? Okay. I'm using my headphone right now. How's now? Still echo?
Yes. Can you turn the volume down on your speakers?
Okay, let me try. How about right now? Is it better? Hello?
Yeah, we still hear an echo.
That's weird. Sorry about that. Maybe, let me see. Try the speaker right now. Hello? How about right now? Did you guys hear the echo?
Yes, Yoon, there's still an echo.
Oh, sorry about that. Which way is better? So, computer, how about this? This good?
No, still an echo. Can you just disconnect the speakers from the computer and just use the microphone and speakers built into the laptop or the desktop?
Yeah, I did. That's what I tried. How about right now?
There's still an echo.
Hello? Can you hear me good?
We can hear you, but there's still an echo.
Oh, I'm so sorry. I don't know what to do. Let me see. But
I think without the headphones is better. I mean, I might be wrong. So
yeah, we tried last time. The headphone, it works fine.
Yeah, can you just disconnect the headphones?
Yes. So now I'm using the computer speaker.
Okay,
that's right now.
There we go.
This is good.
Okay. All right, great. Okay, so I'm not using the speaker. All right, apologize for the technical issue. So in the next 30 minutes, I just get to the point. I'm going to talk about how we can expand the chemical space for the encoded library which I will cover not only the traditional DNA chemistry. So a little bit background, the concept of DNA-encoded library technology was first brought up by Professor Brandon Lerner at Scripps back in 1992. So this is their first publication in PNAS. In 2017, the same author published another paper emphasizing the DNA-encoded library as an open resource, which will be a very powerful path to the new drugs. So this concept actually right now has been broadly accepted by some companies. As we all know, WuXi, Heijin, and XChem, they all have the open DAO program up running. So what exactly happened during the last 2 decades? Actually, not that much until the beginning of 2000. In 2001, New Evolution, which now is part of Amgen, they started their work on the DNA-encoded library. So Praecis started work around 2003, which was later acquired by GSK in 2007. And from then on, you can see a lot of companies joined the field, especially in the last few years. Most of the biopharma and pharmaceutical company and academic group has also joined in this field. Also, there is a really big growth in the DAO literature. This chart summarizes the publication in chemistry alone, starting from 2008. So as you can see, up to 2014, there are really only 1 publication per year or no publication at all. And all these publications are from the academic group, like Mary's group. In the last few years, you can see the publication in chemistry has really soared. For example, 2020, there are more than 20 publications in chemistry alone. Hope we will see, this trend keep growing. The DNA-encoded library technology has 4 cornerstones. First, of course, is the library. I may have some bias since I'm the chemist. In my opinion, library is really the foundation of the technology. What kind of library you have will directly affect the success of this platform. So the second cornerstone is selection, and DAO using the affinity selection to pull out the binders. Because of the nature of the DAO library, it's very understandable that there will be some limitations and not all the targets will work with this platform. So after selection, the next cornerstone is the sequencing and the data analysis and the off-DNA hit confirmation. So all these will be discussed in the future sessions. So hopefully you guys can all stay tuned. So we all know the challenges of the DAO chemistry. It must be DNA compatible and also compatible with water. I will talk more about the water issue later. So to have the high quality library, the desired DAO chemistry must be robust and should avoid the harsh conditions because they may damage the DNA. Also, to make sure that the library have big diversity, the chemistry we developed should be compatible with diversified substrate or large BB set, because this would directly determine the size of the library you can make. And also, it would be good that the chemistry can introduce the new to pharmaceutical space. So to access to a big chemical space, we not only need more feasible on-DNA chemistry, but also we need a diverse building block set and scaffold. So in GSK, for our DAO strategy, currently we like to focus on the increased 3D complexity and good molecular properties. So we use this covalently linked double-stranded DNA for our library size synthesis. I believe currently many of the company and academic group, based on their publication, they also use this piece for their DAO libraries. And we usually install this silver aidol linker as a spacer between the double-strand DNA and the library. And using this amine warhead to do the chemistry to construct the library And on the other end, we will do the enzymatic ligation to encode the building block that's used in the chemistry step. For the library synthesis, we use the split pool strategy. For example, in cycle 1, the starting library material will be split into 96 wells, and then in each well, we will do the ligation, follow the chemistry with one unique building block. And then we pull all these 96 wells together. After maybe deprotection or HPLC purification, if needed, we will get the cycle 1 library material, which will be the mix of the 96 compound, and that can be used for the next cycle. So you can imagine that if each cycle we have one plate, after 3 cycles, we can get almost 0.9 million of the unique compound. Each was encoded with a DNA barcode. With this split pool strategy, you can see that we can very easily make very large of the library. So for the on-DNA reaction, here are some of the general guidelines. First, the reaction, of course, must be DNA compatible. What I'm talking here, the on-DNA reaction, means the aqueous on-DNA reaction. Must be tolerant with water and efficient at the low concentration, for example, 1 millimole or even lower. And the routine condition is 4 degree to 100 degree, pH around 5 to 14. On the more acidic conditions, the DNA will be degraded. And also the chemistry can tolerate up to 70 to 80% of the co-solvent. For example, like acidic nitrite, DMF, DMA. These are the solvents that we usually use to dissolve the building block set. For some of the very water-reactive building block or reagent, for example, anhydride or sulfonic chloride, the challenge can be overcome by using really extra amount of reagent. So typically we're using 40 to 200 equivalent. And this is also the reason why the reaction can be efficient at low concentration, because we really use extra amount of the reagent that can push the reaction to at low concentration. Currently, still there are a lot of areas that are out of reach. For example, we cannot really use in the organic metallic reagent, very strong oxidants, and the acids. So here are the BB that we currently used in our recent library. As you can see, they're huge split size, like more than 10,000 mean, more than 10,000 of the carboxylic acid. So what kind of chemistry really we can do on DNA? Nothing is really elegant, I would say, but they actually cover quite a reaction that has been routinely used in the medicinal chemistry. For example, we can do the CN bond formation, which include the CN cross coupling, CC bond formation, like the Suzuki coupling, Vintage, Adol, Ungi reaction, photoredox reaction, and also various of the cyclization and annulation on DNA. This is really my favorite part, and some of the oxidation or maybe reduction, deprotection. So later I will get into detail on some of the reactions examples. But before I talk these reactions, I want to talk with you first our earliest chemistry, the assay nitrizing chemistry, because this is really a good example to show you what are really the designable chemistry for the Dell library. So the trizing chemistry is not elegant at all, but the chemistry is very robust. And also it's really make us accessible to very large BB set. So for example, the second column can be displaced with more than 11,000 of BB, and the third column can be further substituted with about 6,500 of building block. So as you can see, you can very easily make a million size of the library, which will cover quite a lot of chemical space. So we actually have making maybe more than 10 libraries using this chemistry. And these libraries have delivered numerous hits for very target. So one most successful example is SUH hit. So we identified this hit from a 4-cycle trizing library. So guided by the EOT selection data, we will be able to quickly do the head-to-lead optimization and to lead this lead compound. So the whole process from starting the project and making the protein to deliver this lead compound, it only took about 6 months. And then this lead compound was further to do the lead optimization, leading to this clinical candidate. As you can see, the structure of this candidate is very similar to the lead compound that we have delivered. So this is a really good example to show you that the importance of chemistry to be accessible with large BV and the chemistry to be robust, so which can avoid a lot of the byproduct or unknown product we generate in the library. So the first reaction I'm going to type of the reaction I'm going to talk about is the CC bond formation. So Suzuki is definitely one of the common use of reaction to form the carbon-carbon bond. We found that the palladium tetracase trifenophosphate can catalyze the coupling of the aryl iodide with borates in pretty good yield. As you can see here, either electron-rich, electron-poor, or heterocyclic borates can all give very high yield of the coupling product. So we have done the validation, and then almost 1,000 the boric acid ester can be applied in this chemistry. And also the reaction worked very well with the pyridinol halide, but it did not really work with this challenge substrate. For example, this pyrimidine chloride. Besides this phenoborates, all the others give no yield or very low yield of the coupling product. So definitely this condition can be now used in the library. So after screening the various of the ligand and the catalyst, we found that the combination of the POPD and this ligand can catalyze the coupling of this challenge substrate with various borates. As you can see, all the previous failed boric acid or ester can yield pretty high of the designed product. Also, there are some of the other Suzuki coupling methods being reported. For example, the scientists at the Baylor, they reported using this palladium catalyst to catalyze the coupling of the benzene halide or pyridinol halide. Also, Xu has reported that to coupling with this aryl fluorosulfonate. The good thing is like this reaction can proceed at room temp using the palladium acetate. So Suzuki coupling definitely has been, widely used in the Dell library, but the structure generated is mostly by aryl because the nature of this borates building block. So to increase the 3D complexity, we collaborate with Professor Melanger at UPenn to explore the carbon sp to sp3 coupling using the photoredox chemistry that they have developed in the lab. The postdoc in his lab, James, who now is a GSK employee, he really did a great job to first explore the photoredox reaction with rDNA substrate. And he found that the amino acid radical pregenerator or the DHP radical pregenerator can coupled with the rDNA aryl halide, mostly is a bromide or iodide, using the photocatalyst and the nickel catalyst. The photocatalyst that he used is either this iridium based photoreductant or this organic diol. The reaction that actually can be run on ambient conditions, which is really a big advantage compared to the other photoredox reactions. He also demonstrated that the same radical pregenerator and the silane ways, one can coupled with this trifluoromethyl alkene to generate this defluorinated alkylation product. Recently, the graduate student in the lab, Sharuk, also demonstrate the carbon sp2 sp3 coupling with the alkyne bromide and this silane amine substrate. So of course, there are also other publications on the photoredox. For example, this is the photoredox mediated decarboxylated conjugate reaction to generate this carbon-carbon sp3 coupling product. The same also reported the 2+2 cyclization to generate this cyclobutene, which is pretty interesting. And they also reported the coupling with the alkyne bromide, but using different type of the catalyst. So the CC bond can also be formed by the CH activation. The first CH activation paper was published by Wen from Amgen China, which used this leucemia catalyst. And later, Jin Chuan's lab reported the carbon sp3 hydrogen alkylation of this aliphatic either acid, ketone, or amide with this on-DNA alkyne iodide to form these unique structures, which really cannot be achieved by the other different type of the method. So this is so much for the carbon-carbon bond formation. So next, I'm going to talk about the carbon-nitrogen bond formation. Mostly, I'm going to just talk about the CN cross coupling. We found that this bulk wall pre-catalyst can catalyze the coupling of the aryl iodide with amine in pretty good yield. As you can see from this scope study, the aliphatic, the primary amine give the very good yield of the coupling product. And we were very surprised to find that this imine type of the amine, which was very unreactive toward the other reaction on DNA, actually worked pretty well in this reaction. So this probably will be the first time that we can include this type of amine in the DEL library. So we did the validation of all the amines, and we found that overall it worked very well with primary aromatic amine. But the reaction was not really a very good scope for the primary aliphatic amine. So that's why we decided to further explore Ullmann coupling. So the traditional Ullmann coupling used the copper iodide and the chlorine, but we all know that copper iodide cannot really dissolve in any of the solvent, which will be a very challenging for the library production, especially on the split stage. So that's why we modified the reaction condition. Instead, we're using the copper sulfate and the sodium ascorbate, and we found that both the primary aliphatic amine and the secondary aliphatic amine can give pretty decent yield of the coupling product. So overall, about 800 aliphatic amine has passed validation. Also, the reaction worked well with the sial, either aliphatic or aromatic sial, and also reacted with sodium azide, which will introduce the azide on this benzyl ring, and that can be further derivatized, either can be reduced to amine or can do the click chemistry with alkene to generate the triazole structures. We also found that the Ullmann reaction worked pretty well with the free amino acid. So here are some of the examples. So this is about, what I like to talk about, the CN coupling. Sorry. But of course, there are other of the CN bond formation which can be achieved through the amide bond formation or the reductant alkylation. But I'm not going to talk about that since even though these two reactions has been really routinely used in the DEL library, but you should be easily found in the literature. Next, I will really talk about the heterocyclic ring formation on DNA. And this is really my favorite part because comparing with the scaffold-based library strategy, the heterocyclic ring formation on DNA usually will generate the diversity directly linked on the DNA on the ring system, and also is a much more atom efficient. So the first example I want to talk about is the benzyl imidazole ring formation. So the chemistry is pretty straightforward. We install this scaffold to the DNA through the acylation, floral displacement with the primary amine, after nitrile reduction, this diamine can cycle with the aldehyde to form the benzimidazole ring. So both of these two steps of chemistry is very robust. The nucleophile substitution works very well with aliphatic amine, and the aromatic amine is a little bit, less, I would say less reactive. And for the aldehyde ring formation, both the aromatic aldehyde and aliphatic aldehyde give very high yield of the cyclization product. But unfortunately, most of the aldehyde that are commercially available are the aromatic aldehyde. So which means that the library we generated, majority of the library will have 3 aromatic ring or more, which means that hits generated from this library probably will have poor molecular properties. So definitely we desperately need more of the aliphatic aldehyde. Using the same scaffold and the chemistry, we can also design a different library by linking this scaffold to the DNA through the floral displacement instead of acylation. So look at these two designs. I really like you to think about it. Which one do you like better and why? Right. So the next one I want to talk about is, isoquinoline information on DNA. The DNA, the amine hapiz can react with aldehyde to form the imine, and then this intermediate can react with homophthalic anhydride to form the isoquinoline ring. Since that the imine can be either the Z form or E form, which will generate the either cis or trans isomers. So this happens for the on-DNA reaction as well. For example, when we react with benzaldehyde, we definitely see the 2 peak with a ratio about 1:1. So later we confirm that and create these 2 peak corresponding to the cis and the trans isomers. So as you can see from this scope study, although the reaction work very well for either the aromatic aldehyde or the aliphatic aldehyde. This reaction generated the isoquinoline also have the carboxylic acid function group, which can be further derivatized with amine. So as you can see, you can easily make a 2-cycle library, which will include both aldehyde BB and the amine building block. There are also other interesting rings, for example, oxidizole or imidazole or indazolone ring was reported in the literature. Recently, Schreiber's lab has been demonstrated that the cyclization of this silane derivative on the catalyst of the CCl fluoride to form either 2+2, 2+3, or 2+4 cyclization product. And very recently, Professor Liu, his team has reported the formation of various different type of the ring system, starting from this alpha-beta unsaturated ketone, which can be obtained through the aldokondensation of the aldehyde with different of the ketone building blocks. So I would encourage you to take a look at the paper if you are interested to know more. So far, all the reaction I had talked about here are the reaction that was run under the aqueous condition, which is also kind of limitation for us to access more chemical space. So recently, this challenge has been resolved by 2 teams and the scientists in the Scripps and the Novartis. Almost around the same time, 2 teams reported a strategy of using the solid support to immobilize the DNA onto the resin via the ionic interaction. So Scripps called it IASS and Novartis called APTAC, but the concept is really identical. The only difference is the Scripps using the polystyrene beads that is commercially available, and the Novartis using this modified tannagel beads. So both the immobilized DNA can then go through the reaction under the normal organic conditions. So check out their paper to see what kind of chemistry actually have been already demonstrated on the resin. So this strategy definitely provides us an opportunity to explore some of the chemistry which cannot be achieved before. So another new strategy I'd like to talk about is the micelle promoted process. It has been reported that in the presence of the surfactant TPGS750M, the Suzuki reaction can be run under the condition that no DNA damage was detected at all. It has been also reported that the micelle can very efficiently promote the reverse amidation, which acid was linked on the DNA. So reverse amidation is generally a much more challenging reaction compared with the normal amidation, which DNA was linked on which the amine was linked on the DNA. So it's really very nice to see that, if we can apply this method to improve the reverse amidation chemistry that we often use in the library production. So both strategy, either the solid support or the micelle, I think that both of them will really provide us the opportunity to develop more new on-DNA chemistry. And I'm really looking forward to seeing more paper coming out of this field. So let's see what's it. So far, I have talked about more like a traditional chemistry on DNA. So next, I'm going to really touch a little bit on the non-traditional on DNA chemistry, which is enzyme catalyzed reactions. So under the collaboration with Professor Fritsch at the University of Manchester, we demonstrated that we can do enzymatic glycosylation with the on-DNA substrate. So as you can see, that they can provide pretty good yield of the glycosylation product. Further, we tested oxidation of this carbon 6OH group using the galactose oxidase variance. And we found that this carbon 6OH group can be selectively oxidized to the aldehyde without attacking the other OH group or the OH group on the DNA end. So as I mentioned before that, we still have the challenge to use the strong oxidant because the strong oxidant will attack the DNA side. So this definitely provides us a solution to do more oxidation reaction for the on-DNA substrate. And also, when we look at this reaction, definitely this type of the reaction cannot be achieved by the normal chemical oxidation method. And of course, after the oxide to aldehyde, this aldehyde can be further deliverized using the reductive amination conditions. Recently, Jing Cai from GSK reported also published a paper on enzymatic aldol condensation using the L-threonine adenase. And she found that these two of the enzymes can really catalyze the aldol condensation with various of the aldehyde in pretty good yield. And further, deliveries of this aldol product with OPA and the bulk protected cysteine, Jane was able to resolve the 4 stereoisomers, which was quite amazing. As you can see from this spectrum, both these two enzymes delivered completely 2 different stereoisomers. And overall, you can see that they have pretty good selectivities. So 4 isomers as labeled here, this 1, 2, and 3, and 4. Right. So, for the try to expand the chemical space of the DEL library, of course, one way is really to develop more on-DNA chemistry, but it also is very important that we have for broad of the diversity of the BB set and the scaffold. So to expand the BB set, we can keep buying the building block from the vendors, which is pretty costly. So we also think about alternative way. So we found that the leveraging BB set with off-DNA chemistry is a pretty useful practice. So by converting one function group to another, it will provide us to access some of our scarce building block. So for example, the alkyne is a type of building block is very scarce, not so many commercial available, but we can convert the aldehyde to alkyne using this reagent. And then the reaction mixture of the alkyne can coupled with this on-DNA iodide to generate the very high yield of the coupling product. So here are some examples. So now we have about 2,000 of alkyne that will be available for the Sunny-Rich reaction. So you may ask why we care about the Sunny-Rich product, the alkane, because they actually are the intermediate for the endo ring formation. And also, the off-DNA chemistry will make the inaccessible building blocks accessible. Like for example, the alcohol is type of the building block that cannot be used directly in the aqueous condition because of competition with water. But if we convert it to the activated carbamate ester, and then it can be reacting with the amine hapase in the aqueous condition to form this carbamate. And here is a small scope study. As you can see, both the aliphatic or aromatic alcohol give decent yield of the carbamate product. So last, but maybe also not the least one, is whether we can use the off-DNA chemistry to help access to the building blocks that are not stable in water. Through the premix method, we can convert the unstable reagent to the more stable ones. So I really don't have a good example for this one, but this is definitely the question we are keeping asking ourselves, whether it's possible to do that. So in summary, the on-DNA chemistry development that definitely has been well advanced in the last 15 more years, but I would say it's really still quite limited compared with the traditional organic chemistry. So I still remember back in early 2010s, after we developed the Suzuki coupling reaction, we thought that our next Holy Grail reaction will be the CN cross coupling. So after a few years of struggling, we were very happy that we first developed the CN cross coupling reactions around at that time was around 2015. And 2 years later, when I present at the Scripps in San Diego, I brought up the question about, okay, what was our next Holy Grail reaction? And we thought that it would be the photoredox reaction. For example, the decarboxylated cross coupling, because it would generate very nice structures. But of course, I got different opinion from the audience. So now in 2021, I asked the same question for you guys. What do you guys think? What will be the next Holy Grail reaction for the Dale chemistry? So even though the Dale chemistry, as I talked, still quite limited, but I think it was not that bad because this limitation really can be partially overcome by the diversified of the scaffold and the building blocks. So make sure that we can still can access broader chemical space. So last, I'd like to do a little bit of advertise for the next Dale Symposium, which will happen next year, August 29th to 30th in Boston. And this is a website which is still on the construct. And, I really hope that, we can see you guys there. And if you are interested to present at the Dale Symposium, please contact me. This is my email address. Last, I want to thank the whole GSK EOT community. And also I'd like to thank the organization committee for this great workshop. And thank you all for your attention. I will be happy to take any questions.
Thank you very much, Yoon. I think we probably got time for one or two very quick questions. The first echoes your question on a couple of slides ago. What do you see as the Holy Grail next chemical reaction that's most in need to expand the scope of Dale chemistry?
That's a good question. We have been thinking about that as well. I think that even though we have make the photoredox chemistry worked out, but I still feel there is room for the improvement. And also, I was more looking into the other, like, okay, whether we can use the other chemistry in the DEL, whether we can, for some other chemistry, will we be able to do the flow for the DEL? Will we be able to do the electrochemistry for the DEL? So unfortunately, I really don't have a good answer for what is our next Holy Grail reaction. But another thing is, like, I'm a big fan to form the heterocyclic ring on DNA. So even though I think we achieved quite a lot, like to form different ring, but still there is quite a limitation about the formation of this ring, how the diversity. So if I would say, I would really like to focus on focusing on really to make the heterocyclic ring on DNA. So that is kind of one area I would like to do.
Great. Well, thank you very much for your thoughts on that. It leaves a lot out there for the attendees to think about. I'll go ahead and take us into the break now. We're a few minutes over, and so we are going to take a brief break here. Yoon, if you would address the questions in the comment box. I believe we might be able to, maybe Serene, you can correct me if we can stay online and answer questions in person, but acknowledge that this is meant for a break.